Good morning. Thank you, Sandy, and it's my pleasure to be here. It's really very exciting to see how many people are here, and I was just over in the scientific session this morning, hearing all the latest scientific news, and it's really a great conference. What I would like to do today is to follow up on what Carlos just told you. You did a wonderful job in telling you about how the nervous system works normally. My job is to kind of tell you what goes wrong, what happens to the immune system that then makes it fail to identify the nervous system as normal, and why the immune system starts to attack the nerves and cause damage. So I could very simply say we don't know yet. But that would be very boring. So I'll tell you what we think we know, and we're making progress. So actually a lot of people still feel that, okay, we don't know what causes MS or TM, but the reality is that we know a lot about what's happening, and we're getting smarter every year. Even just since 2 years ago, we know more about the players and the actors. And so to carry Carlos's analogy of sort of a movie or a theater, we're going to talk about the actors, the costumes, the words that go back and forth, and the stage. Much of this has to do with genes that you inherit. We know that autoimmune diseases can run in families, but the genes are not the whole story by any means. So identical twins do not necessarily both get TM or MS or this disease. And in fact, there is a major environmental component. So one of the things that we were talking about next door this morning is how much of it is genetic and how much of it is the environment. What are the environmental triggers? And people like Drs. Hauser and Reich, who have studied all the different genes that could be contributing, are finding that only some of the immune genes may contribute about 10%. And then there are other genes that may contribute to this that we don't yet know. And then we're talking about how viruses could precipitate an immune attack. And so I'll try to go through this. For those of you who've heard me talk before, I'm fond of showing this big picture cartoon. And one of the things I'm fond of saying is that when there are this many arrows pointing this many directions, it really means that we have no idea what's going on here. But it's important to start with theories. And I'm, of course, half kidding, because we really do understand a fair bit of this. And just to orient you, everything that's happening down here between these cells are things that are happening in the blood, or the what we call the peripheral component of the immune system. This is one that we have access to. This is blood cells circulate between the lymph nodes and the spleen and the thymus, and we'll talk about that a little bit. And then they presumably become activated in this area, and then they cross what we call the blood-brain barrier and get into the brain area, which is all depicted here. I'm going to take you through a little bit of this, and I'm going to show you this picture at the end, and I hope that you come a little bit closer to understanding where we are. But there are the actors. One of the major actors are T cells, and we've actually subdivided these types of T cells into what you'll hear Th1 and Th2 and a new kind. And these are the cells that actually recognize foreign proteins, and in the case of autoimmune disease, they get confused and start attacking self-proteins, or your own body. How do they do that? Well, they have to have that protein shown to them somehow. And so there are cells that we call antigen-presenting cells. The antigen is the protein, and it gets presented to the T cell. These cells are actually, I'm sort of fond of calling them Pac-Man cells, for those of you who remember the old video game where Pac-Man would go around chewing things up. These cells are scavengers. Sorry, I keep hitting that. And the Pac-Man cells go around scavenging up proteins or debris, and then they go to the lymph node and they present it to the T cell. And the T cell gets turned on and activated. And it turns out that we have thousands and thousands of different T cells that recognize different proteins in specific ways. And this is part of their costume, if you will, or what they're wearing on their surface determines if they become activated by one protein or another protein. And then they can change their costume, and so they can go from a resting cell to one that's activated and sticky. And sticky T cells will stick to the blood vessel walls. Normally blood is shooting through here very, very quickly, but sticky T cells will bind to the blood vessel wall through interactions with what we call adhesion molecules. and then they can get into the nervous system and cause damage. And of course, in MS and TM, it's the brain and the spinal cord, but in other diseases, those same T cells can go to peripheral nerves. You may have heard of Guillain-Barré syndrome, where people have inflammation and demyelination of the nerves in the arms and legs that Carlos was telling you about, and that can cause demyelination and paralysis just by damaging the peripheral nerves instead of the brain and spinal cord, as in MS and TM. And then there are other autoimmune diseases where these T cells get confused and go to, say, the thyroid and cause low thyroid production or too much thyroid production. And so we're recognizing that there are lots of autoimmune diseases, but we're going to focus on the ones that involve the nervous system. Within the nervous system, there are all sorts of other actors. And so I'm going to introduce you to not only CD4 T cells, but CD8 T cells. And these have dual roles. These can actually be very damaging cells. We sometimes call them cytotoxic cells because one of their major functions is to go around killing things. But they're also turning out to be some types of CD4 and CD8 T cells that are healing or regulatory cells, and I'll show you a cartoon about that. There also are these Pac-Man-like cells that are in the lymph nodes, also exist in the brain, and sometimes we call them microglia because they live in the brain, but they have very similar functions to these cells in the lymph nodes. They can take up proteins and present them to the T cells and cause the process to perpetuate itself or continue to go on. And then there are B cells, and we're going to talk about B cells. These are the ones that make antibody or immunoglobulin, and we abbreviate that IgG. And you'll hear about some diseases today, one in particular called DEVIX, or neuromyelitis optica, where a specific antibody has been found that binds to a new protein that was identified called aquaporin 4 and specifically causes damage in the optic nerves and the spinal cord. And that, of course, is very interesting because we know that these IgGs or immunoglobulins are present in MS spinal fluid and in transverse myelitis sometimes. But in that one particular disease, there's a particular kind of IgG that binds to proteins just in certain locations. So as Dr. Pardo told you, if it binds, it's all about location. And if it binds to proteins that are particularly prevalent in the optic nerves and the spinal cord, then you get this DEVIX process. And so we're understanding now that in this one subtype that some of these IgGs can bind specifically and cause damage. In terms of who's causing the damage, we don't know as much because one of the problems is we don't go in and take pieces of tissue of brain and spinal cord. That wouldn't be such a good thing to do, but and we're fortunate that most people don't die of these things. So we have to infer from models of the disease what's going on or many years later. But we think that sometimes sometimes there can be direct damage by the T cells. Sometimes the B cells make these IgG antibodies I was telling you about that bind and cause damage to themselves. Sometimes they kill the myelin-producing cells, resulting in demyelination. Sometimes there's a direct attack on the wire or the axon. And these macrophages, which are like microglia, they're very similar in the brain, can cause direct damage or direct damage in concert with antibodies. So a lot of sort of complicated things. You also see all these abbreviations here. Immunologists are very fond of abbreviating things because they have long names, but these are the words, really. These are the crosstalk and communication between the actors. And so one actor can talk to another through direct contact, the sticky molecules, or they can send out signals that activate cells from further distances. And so we often call these cytokines or chemokines. These are basically names for inflammatory proteins that are released by one cell and talk to the other cell. So how might this happen? There are three major theories, I think, that through which autoimmunity may happen. And again, we think that there's a genetic predisposition and then a failure of what we call self-tolerance. And normally, our immune systems tolerate ourselves. Just like we talk about tolerating other people, well, it's really important to tolerate yourself and like yourself. And when your immune system likes yourself, it doesn't attack itself. But sometimes it gets confused and loses this ability of self-tolerance. So one of the major theories is what's called molecular mimicry, or what I like to call a case of mistaken identity between an infection and that self-protein. And so normally your immune system is there for a reason. Mother Nature gave you all these white blood cells or immune cells to fight off infections, of which we are constantly being bombarded. Viruses, bacteria, fungi. And so our immune system is always scouring around looking for trouble. But occasionally, one of those viruses that it sees and fights off successfully may look an awful lot like a self-protein. So we're understanding that even common viruses, like the Epstein-Barr virus, which causes mononucleosis, has parts of it that look like myelin. And so that in someone who has an immune system that is particularly aggressive or autoreactive, it may fight off that infection very aggressively and then go on looking for things that look like the virus and attack that. And so that if they can't find any more Epstein-Barr virus, it then attacks myelin proteins. And there are numerous examples. So EBV, or the monovirus, is not the only one. There are many viruses that share similarity with self-proteins. Another major mechanism is what's called bystander immune activation. So again, our immune system is there fighting off an infection, but it accidentally turns on some other cells at the same time. So it's as if you are in a war zone and your immune system is the militia shooting the bad guys, and occasionally, as we know, there's friendly fire and some good guys get hit. So when the immune system's busy fighting things off, there can be activation of other cells that turns them on to do bad things, or the immune system itself may be fighting off an initial virus in the brain and cause damage to tissues as it's killing off those tissues. So there are really sort of two things embedded here that the immune system can do in the setting of an active infection. The final one is release of what we call hidden proteins or sequestered antigens. And so it's known that after damage to nervous system, parts of these self-proteins get released and activate the immune system. And so this would follow an incident, episode of trauma even, although that's never been proven. But maybe more commonly during a bad infection, you sort of stir up the pot a little bit, and so that things that the immune system normally doesn't see on a regular basis, like brain, because the immune system is in the blood and the brain is separated by this protective coating, the blood-brain barrier. If you get an infection of the brain and sort of stir up the pot a little bit, some of those brain antigens, which normally your immune system's not seeing, may actually drain back into the cervical lymph nodes in your neck, and then the immune system sees those antigens that it hadn't seen before. And I'll tell you in a few slides why that may turn it on. So things get more complicated, unfortunately, and so these CD4 T cells, which are sort of the bad guys, actually, as we get smarter, and we know that there are bad guys and good guys, so that we call the effector cells the sort of the militia, and these are the ones that are the bad guys in autoimmune disease, but really the good guys in the setting of infection. They're fighting off different types of infections. I added this slide, so I apologize, it's not in your handout. These are regulatory cells. Okay. The regulatory cells are kind of like the Red Cross. They come in and heal and turn things off, and they're anti-militia. And so there's this constant balance going on in the body with actually all the organs, but the immune system is a particularly good example where you have these cells that are fighting off infection, and then when the infection's cleared, you want to have a way of turning that off. And I just told you that sometimes people don't know how to turn off. So one of the theories here is that these regulatory cells are dysfunctional in autoimmune diseases, and they are not effective at turning off the bad guys when they need to be turned off. Now, why would you have to have different bad guys? Well, just like in the military, you want Air Force, Marines, Navy, all sorts of different kinds of attackers depending on what's going on. And so we recognized that in viral diseases, these Th1 cells may be the most effective. Turns out that in parasitic diseases, Th2 diseases may be important, or even in allergic responses. There's a new type of cell that was recently described called Th17, and not because it was the 17th type, but mostly because it makes one of these communicating molecules called interleukin-17 that seems to be very important. And so Dr. Kerr and I have recently investigated whether blood cells from transverse myelitis patients might be making more of this. So this is in concert with our whole group, and we have found that indeed that in the setting of an acute transverse myelitis that there's a lot of these T17 cells that turn on very early on. And then we asked, well, does the same thing happen in MS? And it turned out that it was not, we didn't really find it in MS, but if we divided the MS into those people who were very early on in the course of their disease versus people who were had MS for many, many years, that's when we saw a difference. And we found that the IL-17 was turned on early in MS. And so we're now finding that maybe this is a type of cell that actually starts the process, and then in MS it converts to this, but in cases of TM which don't recur, maybe you don't get this conversion from one type of malicious cell to another. And so we're getting smarter about that. We're also understanding that there's a little bit of overlap between these healing cells and the malicious cells. So it turns out that occasionally you can take someone who is a healer and make them into a militant type of cell. And there's crosstalk between these cytokines here. There's one that we always thought was good, TGF-beta. In fact, 15 years ago when I was at the NIH, we tried giving TGF-beta to patients because it was known to have healing effects. Unfortunately, it had some side effects which made it us not able to give it to people on a long-term basis. But TGF-beta has always been thought of as a good cytokine that drives these regulatory cells. However, just in the last 6 months, we've found that TGF-beta, in concert with this cytokine called IL-6, drives these IL-17 cells. So we think that we're finding out sort of what turns these on. Dr. Kerr reported last year that in the spinal fluid of transverse myelitis patients, there are high levels of IL-6. And so we're starting to piece together what's turning this on. This is just a little cartoon of how T cells develop. And so immune cells come out of the bone marrow, and that's sort of what we call their preparatory school or elementary school. And at that point, they're pre-programmed. They have their sort of genetic background. They know what they think they want to do, but they're not really very well educated at that point. Then they go to the thymus, which is in your neck. When you're young, your thymus is very active, and it teaches those cells what to do, and it actually sorts them out a little bit. And so it turns out that there's a process called selection, where the cells that are responding to your cell proteins too strongly get weeded out, and they actually get killed. And then the T cells that do nothing, the sort of slacker cells, they get kicked out of school too, because they're not really very functional. And then the vast majority of cells are cells that somewhere are in between, like you and me, that they can be turned on to do good things, and they have to be motivated to do that by the cytokines, but that most of the time they're sitting there resting, waiting for something to happen, living the groovy life, I guess. When they come out of education school here, then they go around and you got to find a job, right? So in this case, the little sign here says antigen, third macrophage to the left. So there's some clues and signals in life. Unfortunately, we're not always left to just drift around. And so the immune system is wired to tell the T cell, go to the lymph node here, and this macrophage will present you with some information about what you're supposed to do next. And so indeed, that's what happens. And this is a little cartoon of the lymph node. The lymph nodes are these things that you feel in your neck when you're sick. They get all swollen up. You got them under your armpit and your groin, and they're all over your body, actually. And different regional locations help to perhaps activate cells that are responsible for that particular location. As I told you, brain antigens can actually drop down into your neck, and so it may be a way of turning on the immune system if you had a meningitis or something. Whereas if you have a local skin infection in your arm, you might get swelling of the lymph node there. Lymph nodes are very sophisticated, and so that there is a part of the lymph node where these macrophage, these buttons are very close together. The Pac-Man macrophage cells actually come in with the foreign proteins that they've scavenged. And so one example is if you get a cut on your arm, you'll have cells that go there and bring that antigen back to the lymph node and teach the T cells, okay, guys, fire up, and there's an infection down there. We need all of you to come over to this part of the body and fight it off. And so they come back to the lymph node. T cells come into the lymph node, and there are signals that bring them together so that these star-shaped cells and the T cells get together, and they decide which ones are going to react in which way, and then the T cells go off and do their thing. Turns out that there are a lot of signals that tell the T cells what to do, and one of the things that we study is how those cells get turned on and why in autoimmune cell diseases they don't get turned off, as I told you about, and so that there is interaction between the antigen-presenting cell, the antigen, and the T cell, what we call a T-cell receptor. And so you hear this scientists talk a lot about these T-cell receptors, but they're also what we call co-stimulation molecules that are on the surface of the cell, and they enhance the process, and so they may make this interaction tighter and closer and allow the cells to become more revved up, or if these little receptors here, these co-stimulation receptors, aren't present, then the cells get less revved up and they're less able to fight off infection, but then they're also maybe less likely to fight off self-proteins or attack self-proteins. And so we're looking at ways of perhaps interfering with the strength of the interaction here as a way of dampening the immune response. How do all these cells know where to go? So that just like in a play, you take it for granted that the actors and actresses are running around all to the right location at the right time. That doesn't just happen without practice. And so in the immune system, again, Mother Nature's very smart and built in a lot of clues and what we call combination codes for entry. And so we're increasingly recognizing that once these cells are in the lymph node and told what to do, that there are patterns of clothing on them or costumes and that tell them whether they should go to the skin and fight off an infection there, or go to the gut mucosa and fight off an infection there, or go to the brain. And so that one of the theories behind some of the MS therapies was that, well, maybe by blocking this one that allows cells to go to the brain, we could prevent immune processes from going to the brain. And indeed, this is what happens with Tysabri, which is a specific way of blocking some of these interactions. However, many of you may know, and I'll talk about this later, that by preventing cells from going to the brain, you're very effective at dampening MS inflammation, but you also allow the brain to become susceptible to a unusual viral infection. And the virus got smart in 1 in 1,000 patients and figured out the brain was a good place to go because the immune system couldn't get there. And so that by messing with this natural immune system, we sometimes pay a price in terms of our preventing our immune system from doing what it's supposed to do. How do the cells get across the blood-brain barrier? This is a whole other area of where there are, I told you about the sticky molecules, the adhesion molecules. They're talking molecules called chemokines that enhance, that sort of say, come over here if the cells are from a further distance away, and attract them. And then there are enzymes that actually digest what we call the basement membrane and allow the cells to chew up part of the blood-brain barrier and make it more permeable or open it up to allow sort of a floodgate of cells. So you imagine that if you're attacking a fortress, you want to knock down one part of the wall and allow all the militia to get in. And the immune system does that to a certain extent, and it renders that part of the wall susceptible to future entry of immune cells. And so there's much interest in trying to understand why that happens and heal that. So once they're inside, how does the damage happen? Well, one of the mechanisms is direct attack by these cytotoxic cells. I told you that these can directly kill cells. They can kill the myelin-making cells, and they can perhaps actually cut the nerve wires themselves. Here's a time-lapse picture of this happening in a culture dish. You can see at baseline the T cell, the cytotoxic T cell, contacting a wire, and then at 15 minutes, 35 minutes, and 55 minutes, you can see that in a relatively short period of time, one of those wires has been cut by that cell. Now, of course, we all have thousands and thousands of little cables within our nervous system, and so that a few we can tolerate, but one of the things that may determine whether one person has permanent damage and another person can come back and walk may be how many of those axons are actually damaged by the immune system during the initial injury. And we know that in MS that this is happening. We see the same thing happening in spinal cord in transverse myelitis. How do the B cells work? I told you that they come out of the bone marrow, and then they go to the lymph nodes as well, and they make these different kind of immunoglobulins. You see IgM and IgA and IgG. The IgM is the earliest kind of antibody or immunoglobulin response that they make, but they can the IgGs are more of an indicator of a chronic process. And so when we take spinal fluid and look for, you may have heard of the term oligoclonal bands. These are immunoglobulins that are being produced specifically in the spinal fluid that aren't in the blood, so that they're presumably is a B cell which matures into a cell called a plasma cell and makes these specific antibodies which can also be damaging. So the B cells differentiate into plasma cells and make these IgG antibodies, but they also have other functions, and it turns out that the B cells can present antigen. They can act like the macrophage cells and present antigens to T cells and turn on T cells. And in fact, one of the interesting things about the Epstein-Barr virus story is that B cells are one of the sources of Epstein-Barr latency. So many viruses infect cells and then can live in those cells for long periods of time. And so pretty much all of us get exposed to Epstein-Barr virus, and then it lives dormant in our body. And one of the theories is that in some people who are more genetically susceptible to certain diseases, that the virus just never gets cleared, and it sits in the B cells, and the B cells then go around and contact a T cell and show it the virus, and the T cells, I think I should attack that. But if it's a part of the virus that looks like the myelin, then it turns on myelin-reacting T cells. And then B cells also give off a lot of these bad words here that turn on cells, so that they make cytokines that turn on the immune system. And so that there's a lot of interest in trying to knock down these B cells. And one of the new approaches to therapy for MS and for neuromyelitis optica is a monoclonal antibody that depletes B cells. It binds to the B cell and kills it. It's called rituximab. And I'll talk a little bit about that in a later talk, I think on Saturday. So this is the final slide, and conclude here that there's a lot going on, so that it's not that we really don't know anything about this. We know a lot about it, and we know a lot about the actors and the words that are going back and forth and the costumes. It's just that every year, as we're getting smarter, we find that it's more detailed. And so just like a lot of things in life, when you're sort of a teenager, you think you know it all. And so I have a 13-year-old son who says, "Dad, I don't know how you get through the day knowing as little as you do about life." And, you know, and it's like the Mark Twain story where he says, my dad learned more between when I was 21 and 25 than he did the first 21 years of my life. And so kids don't know what they don't know. And so actually I would submit that scientists early on in their career don't know what they don't know. And then after you do this for 10 or 20 years, you sort of realize, wow, things are a lot more complicated than I initially thought. But the good news is that with each layer of complexity, we really hone in more, and we can then develop therapies that target that. And so tried to highlight the examples of like how Tysabri blocks the sticky molecules in this part, and then how maybe targeting B cells can knock off a certain component of the disease. And as we recognize that certain subsets of these diseases are mediated strongly by one part, so in NMO or DEVX, it seems to be this particular B cell IgG, and so it makes a lot of sense to use a B cell depleting drug in DEVX because seems to be one of the major problems. But in MS, you got a lot of T cells and other cells as well. Will B cell depletion work? It might work for some people, and if we could be smarter about who has a B cell type of MS or more of a T cell, or who has a mix, we could then design our therapies more specifically. So all of this is obviously very important. Thank you.